All right, so we're going to do number 44, where we have some kind of ultraviolet light that has been incident on a surface. It has a work function, and then we have an intensity of that incident light. We have a speed of electrons that is related to that, and then what is the maximum number of electrons emitted from a square centimeter of the surface per second. All right, so the way that I'm going to do this is first I'm going to kind of think about what does the photoelectric effect mean, what information do we know, what do we not know, and what do we need to actually figure out the final answer. So while my screen gets loaded up here, okay. So photoelectric effect is you have some kind of usually metal surface, and if you shine the right frequency on it, then an electron can get ejected with a certain kinetic energy, meaning that it has the velocity, because it has an energy of motion. Now this has to be the correct amount of frequency, because if you are less than that, right, so you have some kind of low energy, then this will not happen. And if you have more than enough energy, then your electron just accelerates with more gets a velocity with more energy. Okay, so we'll kind of write down what we have. We have, let's see, a work function. So we have our light, we have our electron, we have a work function. And so depending on what the work function of this metal is, then we know what's the minimum amount of frequency that's required to actually create the ejection of the electron. So we're given in the problem that the work function is 3.44. So phi is equal to 3.44 electron volts. And our electrode accelerates to 4.2 times 10 to the 5th meters per second. So that is the V electron. And so from here, we can solve for our kinetic energy, okay? We can use that to find our frequency, because we don't know, we know our work function, we don't know our frequency. And then we can relate intensity, or let's see, what does it tell us? It has an intensity of 0.55 watts per meter squared. So we have intensity is equal to power per meter squared, and power can be related to the energy coming in times the number flux. Okay, so we have meters squared. Okay, so essentially, if we can get the energy kind of per photon, then we can solve for the number flux, that's what it's asking, and then convert it to centimeters, right? So per centimeter squared. So how do we get to energy from this problem? Well, that energy is going to come from frequency, and it's going to be E is equal to HF. So we have everything we need to solve this problem. We're going to go from velocity to kinetic energy, get a frequency, get our energy, and from our energy, we'll plug that in, solve for number of flux, and convert to centimeters squared. Okay, per centimeter squared. All right, so the first step is, okay, what is our kinetic energy? And we can define kinetic energy as, there's more than one way to do it. I'm going to do it this way. So mc squared. So if you remember the original derivation, kinetic energy plus mc squared is equal to mc squared gamma. And so our kinetic energy is going to be our relativistic energy, right? So mc squared gamma minus our rest mass energy. And so this difference should give us our kinetic energy. And we know all these values, so we know that the kinetic energy is equal to 9.11 times 10 to the negative 31 times 3 times 10 to the 8th squared. We can solve for the gamma factor in a second, and then 9.11 times 10 to the negative 31 times 3 times 10 to the 8th squared. So it's good to kind of solve the gamma factor separately, just because it simplifies your calculations. 1 minus v squared over c squared. So gamma is equal to 1 over the root of 1 minus, what was it, 4.2 times 10 to the 5, all squared, all divided by 3 times 10 to the 8th squared. So I'll solve for this first. I'll plug this in, and let's quickly get a kinetic energy value using our calculator. All right, so 1 over the square root of 1 minus 4.2 times 10 to the 5th, and this value is, let's see, this value is squared and divided by, the value is divided by, I know that it's going to be 9 times 10 to the 16, right? Because 3 times 10 to the 8th squared is 9 times 10 to the 16. So our gamma factor is actually 1.024183. So, yeah, I'm just double checking to make sure that, no, it's not. This value has to be squared. And why is it saying it's undefined? Let's see. So this value needs to be squared. I guess we can put it undefined. Okay. It's saying that this is like basically 1, which makes no sense. All right. There's probably some, let's see, 4.2 times 10 to the 5th squared, undefined, divided by 9 times 10 to the 6th. Oh, because this has to be 16th. All right, so that gives me a more reasonable answer, right? Now we actually have a value, and this, I mean, this gamma factor is very close to 1, but it's not 1, right? It's 1.00000. So we're moving at pretty much non-relativistic speeds. So could we have used 1/2 mv squared? Probably, but we'll try to use this number and see what we get. So I will now plug in this value into our kinetic energy formula. So 9.11 times 10 to the negative 31 times 3 times 10 to the 8th squared times our gamma. Okay, so we have some kind of value. And then we're going to subtract that answer, minus 9.11 times 10 to the negative 31 times 3 times 10 to the 8th. All right. And we get a value of 8.199 times 10 to the negative 14. And we don't, because this actually has to be squared. All right. So now we get 8.035 times 10 to the negative 20 joules. So I'll just make a note of that on my thing. So 8.035 times 10 to the negative 20 joules. And we could work with that. Okay, so we have joules. We don't need to convert this to electron volts because we need to find the frequency. Okay, and frequency needs to be operated in joules. So I'll set this up as E is equal to HF minus phi, and our E, our kinetic energy, is 8.035 times 10 to the negative 20 joules, is equal to HF, because we need that frequency, because we need that initial energy, right? This is incident energy. I mean, this is essentially incident energy. So honestly, we don't even need to solve for frequency. We can just solve for incident energy, because we're going to be plugging it in to here, so we don't need frequency. So we'll just replace this as incident energy minus phi. So if we now get our phi in terms of joules, we'll be golden. So we're given that phi is, what is it, 3.34 electron volts. So 3.34 electron volts, where 1.6 times 10 to the negative 19 joules is equal to what electron volts? So let's just quickly plug everything in now. So 3.34 times 1.6 times 10 to the negative 19 gives me that value. and I'm going to add that value to 8.035, so ANS plus 8.035031 times 10 to the negative 20, and that gives me a incident energy 6.1475 times 10 to the negative 19, right? And why did I do that? Well, we just calculated phi in terms of electron volts here, added that to this value, and that gives me EI. So now all we have to do is plug that value in to our intensity is equal to power over meter squared, and power is energy times number of flux. So let's see, intensity is equal to power over meter squared. The intensity was given as 0.55, I believe, watts per meter squared is equal to power, and our energy, we'll write EI times number, all divided by meter squared. So now we can just solve for the number, I believe. So 0.55 watts over EI is equal to number. All right. And so we will know that's the number, and we can, it's like we can keep that in terms of meters squared. There's not, because this answer is in terms of meters squared, right? If we don't cancel it for these units. And so let's quickly plug that in. 0.55 divided by answer is equal to 8.94 times 10 to the 7. 10 to the 17, sorry. And now that's all given in terms of meters squared, so we just have to multiply that 100 centimeters squared over 1 meter squared is going to give us the value in centimeters in per, or I guess we should do this opposite, right? So 1 meter squared is equal to 100 centimeters squared, because we want it per centimeter squared, and so that gives us a value of answer divided by 100 squared, 8.946 times 10 to the 13 per centimeter squared. So this is the number of photons that are incident per centimeter squared. And it also means that if we had this many photons in, then we're going to have this many electrons out, since it's a 1-to-1, since they all meet the work function, assuming it's a perfect world. All right, so let me know if you have any questions from there.